Today, education is expanding in scope across the world, and India takes the pride of place in it. In South India, Tamil Nadu and its capital city Chennai, on the shores of the Bay of Bengal, is one of the biggest centers for culture, economics and education. Carrying forward its heritage, Chennai has emerged as a modern hub for quality education, and Saveetha University is the leading and most sought-after destination here.
You're now in India as one of the topmost engineering college. It's a house for 3,000 students and 8 departments. All the 8 departments offers graduate, postgraduate and PhD programs. We are starting with 3 more departments: electrical and computer science, biomedical engineering and bioinformatics. The engineering school is a 7-story building with 74 high-tech classrooms with facilities like smart boards and Wi-Fi networks.
Part of studying in Saveetha School of Engineering? Well, the answer is SFS, Study Flex System, where we have the liberty to choose our course, timings and our faculty.
Saveetha Learning Resource Center is a hallmark facility that houses thousands of books, e-journals, digital learning resources, discussion rooms and reference sections. Could you ask for more to inspire self-motivated learning?
Saveetha graduates undergo 2 compulsory internships every year. Industry-relevant projects and intensive lab hours ensures that Saveetha graduates are industry-ready.
I like the regulations here, which helps me to score credits for publication of research papers in peer-reviewed journals.
The world is bridging engineering with health sciences through biotechnology and bioengineering. I think Saveetha has an edge here because of its preeminence in medical education.
Today, education is expanding in scope across the world, and India takes the pride of place in it. In South India, Tamil Nadu and its capital city Chennai, on the shores of the Bay of Bengal, is one of the biggest centers for culture, economics and education. Carrying forward its heritage, Chennai has emerged as a modern hub for quality education, and Saveetha University is the leading and most sought-after destination here.
You're now in India as one of the topmost engineering college. It's a house for 3,000 students and 8 departments. All the 8 departments offers graduate, postgraduate and PhD programs. We are starting with 3 more departments: electrical and computer science, biomedical engineering and bioinformatics. The engineering school is a 7-story building with 74 high-tech classrooms with facilities like smart boards and Wi-Fi networks.
Part of studying in Saveetha School of Engineering? Well, the answer is SFS, Study Flex System, where we have the liberty to choose our course, timings and our faculty.
Saveetha Learning Resource Center is a hallmark facility that houses thousands of books, e-journals, digital learning resources, discussion rooms and reference sections. Could you ask for more to inspire self-motivated learning?
Saveetha graduates undergo 2 compulsory internships every year. Industry-relevant projects and intensive lab hours ensures that Saveetha graduates are industry-ready.
I like the regulations here, which helps me to score credits for publication of research papers in peer-reviewed journals.
The world is bridging engineering with health sciences through biotechnology and bioengineering. I think Saveetha has an edge here because of its preeminence in medical education.
Today, education is expanding in scope across the world, and India takes the pride of place in it. In South India, Tamil Nadu, and its capital city, Chennai, on the shores of the Bay of Bengal, is one of the biggest centers for culture, economics, and education. Carrying forward its heritage, Chennai has emerged as a modern hub for quality education, and Saveetha University is the leading and most sought-after destination here.
You're now in India as one of the topmost engineering college. It's a house for 3,000 students and 8 departments. All the 8 departments offers graduate, postgraduate and PhD programs. We are starting with 3 more departments: electrical and computer science, biomedical engineering and bioinformatics. The engineering school is a 7-story building with 74 high-tech classrooms with facilities like smart boards and Wi-Fi networks.
Do you know the best part of studying in Saveetha School of Engineering? Well, the answer is SFS, Study Flex System, where we have the liberty to choose our course, timings and our faculty.
Saveetha Learning Resource Center is a hallmark facility that houses thousands of books, e-journals, digital learning resources, discussion rooms and reference sections. Could you ask for more to inspire self-motivated learning?
Saveetha graduates undergo 2 compulsory internships every year. Industry-relevant projects and intensive lab hours ensures that Saveetha graduates are industry-ready.
I like the regulations here, which helps me to score credits for publication of research papers in peer-reviewed journals.
The world is bridging engineering with health sciences through biotechnology and bioengineering. I think Saveetha has an edge here because of its preeminence in medical education.
Good day, Dr. Mario. You hear me? Good day. Good day, Professor. You have to unmute yourself, Professor. Please unmute. Okay.
Good morning. Hello.
Yeah, Dr. Mario, how are you?
I'm okay. I'm fine. Thank you very much.
Okay. Thank you very much for joining today. I know it is very early today there, and thank you very much for your time. We'll start very shortly. We are expecting a few more participants to join, and maybe initially we can do the setup. Maybe you can share your screen and keep the first slide. Then I will do a formal introduction. Then you can start your presentation.
Okay, perfect, brilliant. I will start sharing my presentation.
Yes, please.
Can you see my presentation, my first slide? Okay, good.
That's perfect. Let's wait for 2-3 minutes, then we'll start the introduction part.
Yes, sure.
Let's give some time for the participants to join. Yeah. Well, welcome you all to the International E-Conference, and this is going to be the first keynote talk. Frame sir, whether I am audible?
Yes, sir, your voice is audible, sir.
Okay, thank you, ma'am. Okay. Very good afternoon to all of you. Today we are going to have the first keynote session now. The speaker of today's session is Dr. Mario Gianni. He is going to address on the topic autonomous and intelligent robots in real-world domain application. Let me go through about the Dr. Mario Gianni's profile. Dr. Mario Gianni has been a lecturer in computer science and robotics in the School of Computing, Electronics and Mathematics at the University of Plymouth since September 2017. From April 2015 to September 2017, he was assistant professor at DAAG Sapienza University of Rome and member of the ALCOR lab led by Professor Fiora Perry. From 2014 to 2017, he worked for EU, developing new science and technology for long-term human-robot teaming for robot-assisted disaster response. He designed a framework for autonomous exploration, patrolling, and coverage of rescue scenarios for a team of heterogeneous robots. In 2016, he developed a team of ground and aerial robots to collect data for 3D textured model of the interior and exterior of two churches in Amarese, Italy, badly damaged by an earthquake. From 2010 to 2013, he worked for EU, aiming at providing natural cooperation between humans and teams of robots in urban search and rescue scenarios. Recently, he has been granted by EPSRC National Center for Nuclear Robotics project via a flexible partnership fund in collaboration with Babcock International Group to undertake the collaborative research towards the development of a framework for autonomous robotic inspection and radiological characterization of the interior of various size, multipath, and non-planar steel pipes. Dr. Mario Gianni also received a grant funded by Innovate UK for the knowledge transfer partnership between the University of Plymouth and AP Precise Pool Limited. The main objective of this project is to develop enhanced automation, mobile navigation, and situational awareness for remotely operated vehicles for explosive ordnance disposal. Finally, he has been made a grant by the School of Computing, Electronics and Mathematics, University of Plymouth for a project titled Hydrobates, long-term UAVs blade inspection in offshore wind farms. This project aims to create research opportunities at the University of Plymouth in the development of autonomous unmanned aerial vehicles for long-term blade inspections in offshore wind farms. Dr. Mario Gianni has published over 30 academic papers. He has served as peer reviewer and as committee member in several international journals and conferences in robotics, including SSRR, Autonomous Robots, IROS, ICRTECC2020, and the Journal of Field Robotics. I am very happy and proud to welcome Dr. Mario to give his keynote talk today on autonomous and intelligent robots in real-time domain application. Please go ahead, Professor. Yeah.
Thank you very much for introducing me. In this talk, I'm going to present our current research activities at the University of Plymouth involving robotic technologies, and not only, as we will see, in different kind of domain applications, with the main strand of improving and increasing the level of autonomy and the capabilities of those complex systems to achieve large-scale human tasks and in collaboration with humans. I think that I could skip a few additional information about me, as the introduction was quite exhaustive about my previous and current research. And let's just go immediately into the core of this presentation. Here we will go through different robotic application, as I was mentioning, and we will see through different videos and other images how we moved toward the design and developments of robotic systems for urban search and rescue applications, for disposing bombs, as already mentioned, and in particular for also applications involving agriculture technologies. Another new recent trend in robotics that is developing here at the University of Plymouth is related to automate the inspection and maintenance of offshore renewable energy devices. This is quite a very interesting domain application at the moment for the University of Plymouth. And then we will go through other research in robotics that are related to telepresence, virtual reality, augmented reality, and social robotics. Autonomy. Autonomy is one of the main important aspects if we want to really see our robots moving far from our laboratories and do complex tasks jointly with humans in real domain applications. Here you can see, okay, how we tried to use aerial vehicles and grounded ones to explore the interior of a collapsed church, with a particular focus on acquiring enough data to provide the firefighters with an initial assessment of the conditions. Here, robots have been used in an autonomous modality that we commonly call shared autonomy, where some of the tasks were autonomously performed by the robot, while others were in charge of the human operators. And by mixing those two kind of interventions, we were able to achieve, the mission of exploring these complex environments, okay, without basically lose our technology. Because in those kind of scenarios, one of the important aspects is that the technology can be considered, must be considered expendable. In those cases, if we were losing robots, it was very, very complicated and difficult to go there and retrieve. So here, just to give a flavor of autonomy, but thinking in terms of very simple behaviors, like be able to return back to the remote command post in case of any sort of failure, those kind of very simple behaviors, you can imagine how very effective can be in those kind of situations. Here, another example where two different kind of robots were collaborating each other to explore another church, in this case in a completely different place and also in a completely different kind of earthquake, where firefighters were not allowed to enter. And here we used basically an approach where we were mixing the sensors, the perception coming from two different robots to enable the situation awareness of the human operator, which was remotely located outside and not in line of sight with the robots. Very interested in this kind of mission, real mission, in-field mission. A very interesting experience was exploring the collaboration of multiple drones of different size, okay, to be able to pass into narrow passages with a very low visibility. And in this kind of example, the bigger drone was flying on top of the smallest one to provide the operator with a third view of the smallest drone, which then was able to fly inside through the damaged roof of that building. We moved toward the application of those kind of technologies in different domain applications. And here you can see how those technologies can be easily applied and fit for the purpose of improving the autonomy of vehicles used by Army, Navy, and police for disposing bombs. And here, this is a robot named Guardian, and is a tracked robot. And the locomotion system of this robot enable it to climb, basically to pass over very complex 3D shapes, okay? And also very high compared to the rest of the platform, which are similar to it. And it is endowed with a manipulator, which is used basically to carry an end effector for disposing explosive devices, I mean, located, for instance, in this example, under a car. And here, where basically we direct our research to achieve those main objectives, having a mechanical system, which might be a wheeled, which might be a flying robot, which can be a legged robot. How can we enable those different platforms with different locomotion systems of a different level of autonomy and with the ability of performing tasks similar and in collaboration with humans? The first front is the perception. Building a semantic representation of the environment using the data coming from the different sensors mounted on top of a robot is quite crucial to enable a robot to reason about actions in a real world. Here we are talking about models of the environments where the robot can take a decision, can use to take a decision. We are talking about those representations in terms of geometrical representations, as you can see on top left of the video, where a drone was flying inside an abandoned facility, and using the scans from a laser, it was able to reconstruct a 3D shape of the internal of this facility. This representation to enable autonomy of a robot might not be enough. We would like to have something more similar to a human representation. So most of the work that we have done and we are doing is increasing this information. And for instance, here you can see several examples where from simple geometric information of a scene, of an unstructured scenario, we were able to extract information like this area is fully flat, this area is a wall, and those are highlighted by different colors, green and red, that you can see in the videos. Or for instance, this area is connected into through different kind of paths to another area, so it can be navigated. Or this area can be safely navigated because based on the kind of locomotion of the robot and the constraints of the scenario, the robot can safely navigate on that kind of surface. Can also deal with dynamic obstacles and easily update a scenario and reason properly about that. Taking care, for instance, also of the communication or the connectivity. When we want a robot to be autonomous, we need also always to consider what is the communication infrastructure that we are using. And in order to enable our robot to be autonomous, okay, some intelligent behavior must be in place to manage any sort of communication loss. On top of the perception, to move toward autonomy, it's quite important to introduce to ground any sort of reasoning about spatial movements. And in this case, we moved our research toward the design and implementation of algorithms, enabling robots to move on different kinds of surfaces and to easily generate paths on these difficult surfaces, in particular in 3D, not simply in a 2 dimension. But on top of this, we are also interested to build some cognitive level of control, where a different form of intelligence can take place, like, for instance, mechanism to enable a robot to take a decision on whether or not to return to a base station due to low power of the battery or due to a fault in the communication, while, for instance, it was driving toward an area where a possible victim was located. Those kind of decisions which require, as you can imagine, an high level of information, and this level of information is extracted from the perceptual block that we were describing before. We want to increase our platform with a good capability of moving. So we need to enable any sort of robot to understand the kind of interaction with the environment. And most of the time, in order to keep the cost of our robots quite low, we cannot really have on top of our platform a particular kind of sensors which would enable us to get this feedback. So we needed to estimate those feedback from other different data and sensors which are on the board. And in this case, for instance, a clear and simple example is how can I improve the motion of a platform on top of a staircase if I cannot estimate the contact of the subtracks with the stairs because I don't have any sort of sensor. Here, we move toward the application of machine learning techniques to estimate those kind of feedback using data, for instance, from the motors and from the sensors. These applications, these technologies are also quite important in other domain applications, not only in extreme environment, as I was mentioning before. And here you can see an example of our research where we grounded these technologies also on a robot which has been recently designed by Saga Robotics, this company. This robot is named Torvald and is used for agricultural applications. One main particular characteristic of this robot is that it's a reconfigurable robot. So the robot can change the length and its size because it's endowed with linear actuators. So this means can adapt also to the size of the paths. And here you can imagine how must be important for us to extract from the sensor data of the robot information like how wide a path might be or how tall a wall can be to enable, the robot to get to assume the right configuration to move in that particular passage. Another important research in agricultural robotics which involves autonomy but not mobile platforms, in this case manipulators, is this kind of application developed by our colleague Martin Stollen, where here is robot, the gummy heart, he designed a few years ago, is autonomously picking up a tomato in a training area using, this soft robotic arm. As you can see here, autonomy for us also involves the design and the development of bespoke devices to optimize particular tasks. Other important strands of research which are currently active in our university are related, as I was mentioning at the beginning, to offshore renewable energy, maintenance and inspection. In this context, here there are two research projects recently started. One is using large-scale drones, in this case hexacopter, to inspect the blades of the wind farms. And in the second project, instead, we are trying to extend this model of collaborations, also involving different kind of platforms like vessels. Now here in this research is very interesting. One of the main problems that we are trying to deal with is not in terms of the hardware, in terms of the technology, but more in terms of the control. So in those kind of scenarios, the weather conditions actually are so difficult, where traditional approaches for controlling those platforms are not enough. And most of the work here is to try to have in place a sort of predictive control which could compensate, the perturbances and make more stable, the overall controller of those platforms, including, for instance, the landing and the takeoff of the drones on top of the vessels. Here in this video, you can see some of our initial results on this boat, the Springer, where we used the side scan sonar to map the bed of this river. And this is our initial results in terms of autonomous mapping using the side scan sonars. And this research work is carried by our Autonomous Marine System Research Group, led by Dr. Sanjay Sharma. One very interesting research that we are undertaking is the design and development of platforms, robots, for the inspections of the interiors of pipes, where the diameter can change, where we could have different kind of bends, and also where we could have upwards and downwards pathways. The main purpose of having those platforms is to build the radiological mapping of the internal of those pipes, to facilitate the work of Babcock in dismantling the reactor compartment of nuclear submarines. Now, this is a really serious problem because there is no technology at the moment in place which can really cope with all the possible requirements and the constraints of the pipeline system. And here we have developed different kind of platforms and robots, as you can see from our initial preliminary tests, where at the beginning we were thinking we had developed a stunt race drone, micro race drone, and then we moved on a caged version of it. And in parallel, we were also exploring different kind of actuators mounted on the tracks of a robot. In this particular case, we tested the magnetic one. While here, in the context of the control, you can see our preliminary results in terms of flying with the drones inside very confined spaces, and how basically the approach using the proximity sensors on top of the robots could be used, okay, to determine, okay, the boundaries. And here, for instance, an initial study of the strategies of moving the robots were also conducted, where, for instance, we're suggesting that turning should happen, for instance, quite early in advance, in case the robot was moving from one level to a different other level. This would reduce, I mean, a lot of the instability while passing through the pipe from the bottom to the top. In the context of automation and manufacturing, we are very keen to introduce autonomy for supporting productive chain or creative making. In this context, we also, in collaboration with the School of Art and Digital Art, we won this prize, this competition, international competition, where Epson granted us with the 3 robotic manipulators. And in the context of this competition, we developed, and we are still developing, different kinds of projects. One is related to mimicking the artwork, the human artworks, where here the idea was to enable a user to design an end effector for the robot using 3D printing techniques, as you can see here, then mount these different kind of support. And here, as you can see, the support is not necessarily had to have one single hand for one single paintbrush, but can also have different ones or of a different shape, mounted on a robot, and then, okay, try to mimic echoing one particular more human painting. Here you can see that we tried to use this example as our test, but we have many of this, where we acquired using an RGB camera system the image, the human work. Then this image was synthesized and transmitted and transformed into joint motion of this 6-arm manipulator. And then, okay, this was basically the results that the robot was enabled using the algorithm and the drawing strategy that we implemented. This was the results that we got. And here you can see how robot using our approach was able to mimic the real painting. And here you can see clearly the results. In the context of automation and manufacturing, an important aspect is telepresence. This is a very crucial point in the wide range of the autonomy, in particular now in the context of COVID-19. Imagine to have basically to remotely control simply from home a robot and do your job from home and assembly a piece, okay, on your productive chain. Very, very simple. And you can do that by controlling another robotic arm exactly equal to the one that you have in place and mimic your motion onto the remote one. This is what we are trying to do here in terms of developing remote telepresence, where, for instance, in this video here, there is an example where our colleague was trying to push one arm, and the arm on the right, his right, was simulating the motion. This technology, as you can imagine, can support enabling the social distance, okay, in working environments. And this is one of the recent research projects that we submitted. In this context, it's quite important to provide the human with an immersive experience. That's why we moved toward the integration in this remote telepresence control of VR and AR technologies. And here you can see our colleague, Dr. Chung-Soo Lee, who is demonstrating his framework for remotely control through a visual system, and using and tracking the motion of his arms, he can control the Baxter robot, which is one of the humanoid robots that we have in our department. His work also here to demonstrate how an haptic interface can, be paired to control the second arm of the robotic of the Baxter. And on the right, okay, moving, controlling through visual feedback, the fingers of the hand. Historically, we have a long legacy in social robotics, where a lot of work has been done to enable with cognitive and intelligent behaviors robots like the iCab, Pepper, the Now. We also are at the moment rising the robot football competition. In particular, last year, I have also introduced a new module in the bench of robotics to start introducing humanoid robots. But here instead, in this video, one interesting aspect is that in terms of social robotics involving robots in healthcare, we are also moving a little bit far from the idea of having humanoid robots. And we are also thinking about having different kind of robots, where here, for instance, you can see a robot which is completely different from any sort that what we have seen so far, and is basically on the idea that, okay, we may have a new generation of social robots, okay, to cure, for instance, dementia. And this robot is really very simple, but it reacts quite sensibly, okay, to the human behavior and to the living space of the humans. And this is our current research carried by our colleague, Dr. Svengel. Finally, to conclude, just to have a bit of fun with our students, which try to apply what we teach in terms of autonomy and in terms of robotic design for creating these robotic competitions, where they created their own kind of robotic platforms of different kind of shapes and with different kind of tools, and basically they were trying to fight each other. And this is one of activities that we also our students are really very keen with our support to manage and carry. Here it's very interesting because again, one of our main interest aspect is moving from a traditional view of seeing the robotic platforms and the mechanics and the electronics and thinking about always differently from what is at the moment is considered. Yeah. And this kind of work is supported by our senior technician, Jake Gibson-Sutton. Thank you very much for your attention. And from my side is all. Any questions?
Thank you, Dr. Mario. It was really indeed a wonderful presentation You showed us various types of robots, various forms, various applications. I'm sure our faculties and students would have been much benefited, and we are also live Facebook. So many of the students and faculties are also seeing through Facebook also. Now let me open the forum. Anybody is having any queries, you can ask now.
Can I stop sharing my screen?
Yes, yes, please. Anybody wants to ask any query, question, you can raise your hand. Yeah, and then we'll unmute and ask the question. Okay. Before they get ready, let me ask one quick question. Like we were in a plan of designing few paper robots, like paper robots. So robotics in like humanoid robots for other applications as well. So how far you have progressed in that, and what are the possibilities of collaboration between Plymouth and Saveetha? So can you highlight on those lines? It will help. Yeah.
Yes, the work at the moment, our paper robots are actually, I could show you if you want me, because I have other 3 little videos on paper. Can I share with you?
Yeah,
Good.
please.
I have 3 different videos about at least showing our current okay. Yeah, because those videos are okay. Yeah. Okay, can you see?
Yes.
Okay. This is one interest application.
I spent a lot of time at the University of Plymouth, but I'm a robot, and I want to hear what it's like to be a student here. You have seen this around your campus. You just need to follow the link to the survey and answer questions about your university experience.
Here we extended the speech recognition and the language package of the paper to introduce more functionalities very, very similar to the ones that are used in museum. And here we were applying those technologies for improving, the student survey. Here instead, okay, in this other video,
working here as a roboticist, working on human-robot interaction, how to get those little things to do things with us in a way that seems to be kind of natural. And this thing here, this tail touch screen, is something we use to run experiments with children in schools. So, for instance, here right now I have this other tablet. I can send orders to the robot. So if I move the giraffe here on the screen, you'll see the robot's trying to move it on the screen. So if I do the same thing with the ball up, it's going to look at the ball and move it around.
Those are, and here where we extended the cognitive, package of the now to enable with more complex reasoning and also to integrate with the different platforms. In that case, it was introducing an external screen and also the touch screen plus the reasoning system on the map.
Very interesting, and I'm sure a lot of things.
In terms of movement, I think that I don't have to say anything else because I already showed that we could move robots around.
Yes.
In terms of intelligent behaviors,
and I'll also share your mail ID with your faculty members, so that in case if they have any queries, they can always post it to you. And we can also collaborate I can connect few faculties from Saveetha so that we can collaborate and then look into develop these kind of robots together in the future. Yes. And thank you very much. It's really an honor for us to host you today, and thank you very much for accepting in a short span of time, and you have given us a very good insight of the possible applications of robotics in various fields. That too, interestingly, painting robot, humanoid robots for human beings, and many applications you have showed, which are all very interesting and fascinating. So thank you very much, and looking forward to your long-term collaboration. Thank you. Good day to you.
Thank you very much. Have a good day to all of you, and thank you again for the invitation.
Thank you. Thank you very much. Good day.
Bye.
Bye. Bye. Very good afternoon, Dr. Mazira. Radhika, ma'am?
Yes, sir.
We can go offline, ma'am, for 10-15 minutes so that we can do the setup for the next speaking.
Start the session by 2:15. Is it okay?
Yeah. Yes, ma'am. The speaker has already come, so we have to do some setup, and then we can go online again.
Next keynote session by 2:15.
Yes, ma'am. Yes.
Thank you.